Hello everyone, we will solve another magnetic circuit example. Again, we have single loop with different dimensions and we have single source which is located on the left leg. So according to dimensions, when we check the circuit, we have two different widths. So for the top leg, we have 15 centimeters, and for the others, we have 20 centimeter width for this figure. So that means we have to separate this two parts from each other when we are writing the reluctances. And in addition to that, we have to remember we have the air gap reluctances because of the remained air gaps for the left and the right leg sides. So let's start with the magnetic circuit drawing. So we have single source which is located on the left side. So through the magnetic circuit, first of all, we can start with the air gaps. For example, all the reluctances will be connected in series so that their places are not will not change anything. So we have two air gaps. So two air gap reluctances we must write for the left and the right side of the circuit. Then we have the small part. For example, for this part, for the top leg, we should define another reluctance. Let's call it as R1. And we have one more for the big part, which has 20 centimeter width. And it can be R2. So in the magnetic circuit, we need to draw two more reluctances to represent R1 and R2. And our magnetomotive force value will be N times I. So if we start with the RA calculation, air gap reluctance, our numerator will include the mean path length, which is the width of the air gap, and it is 1 millimeter. Then, in the denominator, we have, first of all, relative permeability of the air gap, and it will be 1 with respect to free space permeability value. And we must multiply it with nu zero, which is 4 pi 10 to the minus 7, and it is the free space permeability. Then the cross-sectional area will come. What was the cross-sectional area? We need to write the width of the air gap and depth of the air gap. We must multiply. So the dimensions are 20 width, 10 depth, and the result must be converted to meters square. According to this, we have 39,809 ampere turn over Weber for the air gap reluctance. Okay, let's continue with R1, which is the reluctance of top leg. Again, for the numerator, we must write the mean path length of R1. So for the dimensions, only for the corners, we will take the half of the dimension. So let's start for R1. If we start from the left side, our dimension for the left corner is 20. So we will start with 10, which is half of 20. Then for this part, we must take full dimension, which is 60. Then again, similarly, we have half of 20, which is 10. So 10 plus 60 times 10 must be converted to meter. All the dimensions for the core part are given in centimeter. So we convert it to meter again. For the denominator, we have 1,500 relative permeability, and the next term will be the 4 pi 10 to the minus 7. For the cross-sectional area of this part, our width will be 15 centimeters and the depth is 10, and meter square conversion must be done. We have 28,308 ampere turn over Weber for the first reluctance. Then we have another part which looks like a letter U. So for that part, we can continue with its dimensions. So for R2, we will follow the purple dashed line. So if we start from here, we have a small part for the I part, also for this big part, because we have still 20 centimeter width for all part in this leg. So we will analyze that part completely for the left side. Until to that part, we must analyze the figure. So we have a letter U for the analysis. For EI form, or UI form, if we start from here, that part, we have half of 15, then 80 for the big part. Then for the left bottom corner, we have 10 and one more 10, which are half of 20s. And 60, 10, 10, 80, and lastly 7.5 will come to the mean path length calculation. So we will start with 7.5. Then for the long part, we have 80, we have 2 10s, and 60. Again, for the right bottom corner, we have 10 and 10, 80, and the last part will be the 7.5. Again, we converted to meter, and for the denominator, we have the same values except cross-sectional area. So when you compare U part with the I part, widths are different. So because of this, we separate their reluctances. So for the cross-sectional area, the width will be 20 instead of 15. And we will multiply by 10, which is depth, and 10 to the minus 4. So 72,983 ampere turn over Weber will be the second reluctance. And according to our magnetic circuit, we can now calculate the total equivalent reluctance value. So for our total or our equivalent, we have two RA, two area reluctances, R1 for the top side I part, and R2 for the remaining U part, which is the biggest reluctance in the circuit. So totally we have 180,909 ampere turn over Weber. Now the question is, if we apply 1 ampere to this winding, according to our calculations, what will be the flux value? Okay, for the flux calculation, flux is the similar parameter of current in electric circuit. So we can use the magnetomotive force, which is the total source of the circuit, divided by total resistance, which is the reluctance of the magnetic circuit. So our total can be written. And the numerator parameters are given, which are 500 and 1. Our total we have calculated. So from here we can find the flux as 2.8 milliweber. And in addition to that, this is the flux which is flowing through the circuit. In addition to that, in the different cross-sectional area parts of the circuit, we can determine the magnetic field density values. For example, if we want to calculate the magnetic field density for the left leg, which the winding is located, so for B winding, let's say, winding located leg for the left leg, our expression must be flux over cross-sectional area of this leg. So flux is the total flux. In everywhere we have 2.8 milliweber. And for the cross-sectional area of the left leg, we have 20 centimeter width, 10 centimeter depth, and we must convert to meter square again. So 0.14 Tesla, according to the given parameters and the dimensions, can be created as magnetic field density on the left leg, which we located our winding. Thank you for watching.